Okay, so the main thing kind of underlying the Oneida lemma is this sort of isomorphism here. This idea that you can go from an E-type element of X to an arrow from Hom E comma blank to X, an arrow which we call, in this case, theta under arrow. So let's suppose we have some E-type element of X, theta, in mind, and we want to create a natural transformation theta underlined according to the Oneida construction. Well, I haven't told you what the Oneida construction is in this video yet, so I'll do it now. And it's really a very pleasant idea. The idea is just, well, we know that we want theta underlined to be a natural transformation from Hom E comma blank to X. In other words, we know we want theta underlined to be the kind of member of this set of natural transformations, which is kind of in correspondence with this E-type element of X theta here. Okay, so we want to find this natural transformation theta underlined. So we know it's a natural transformation. So we know that, for example, its eth component, theta underline E, is going to be a function from Hom E comma E to Xe. We know that its vth component is going to be a function from Hom E comma V to X of V. And being a natural transformation, we know that for any arrow S from E to V in our general category C, we know that this kind of square has to commute here. So what we do, we basically are going to think about these four different kind of functions involved in this square and the fact that this square should commute. So the way we're going to think about this is to think about elements. So all we need to kick things off is an element of Hom E comma E. Well, there's an obvious choice about where to start. We can start with, how about the identity arrow of E? Well, that's always going to be in Hom E comma E. So let's think about what happens to that. Now, it turns out that in order to define this natural transformation theta underlined here, all we have to do is just make one choice. Okay, so if we think about this kind of square, then we know that the identity arrow of E is going to get mapped to some element of X of E under the eth component of theta underlined. Now, I haven't really told you what theta underlined is yet. I'm sort of defining it right now, but I'm saying at least it is a natural transformation from Hom E to X. Okay, so we know that its eth component should send the identity arrow of E to some element of X of E. And I'm saying we want to basically start with theta, and we want to make this natural transformation theta underlined. So basically, in order to do this, we just have to make one choice about the construction of theta underlined. And that choice is just, where does the eth component of theta underlined send the identity arrow of E to? In other words, we just have to select what the value of, in other words, we just have to select what value we get when we do the eth component of theta underlined on this identity arrow. And in order to get this kind of natural transformation theta underlined, which is sort of in correspondence with theta according to Oneida's theory, what we do is we decide that we're going to send the identity arrow of E to theta, okay, because theta is an element of X of E. And so it turns out once we make this choice, it's very remarkable that everything else about this natural transformation is then kind of forced into having a particular form, okay? So let's see that. So we're supposing that we're working with general category C, and we're supposing we're thinking about a general arrow S from E to V, okay? And we're thinking about this naturality square. And, you know, of course, this has to be a commuting square if theta underlined really is a natural transformation. And so we have to have that, you know, doing these compositions here has to give us the same function. Or if we like, if we loaded in an element at the top left and did the functions going along the right and the going along the top and the right, we'll get the same output as if we do the functions going along the left and the bottom. So let's just see this then. We've already said that we're going to send the identity arrow of E to theta under the ETH component of theta underlined. And then if we do XS on that, then of course we get XS of theta. So that's going along the right and the bottom. So that's going along the top and the right. Okay. Now going the other way around the square, if we start with the identity arrow, well, going this way around the square, we ought to do hom E comma S on the identity arrow of E. That just yields S. And then if we do theta underlined, if we do the VEEF component of theta underlined on S, we get, of course, the VEEF component of theta underlined operating on S. And since this is a commuting square, that has to equal the other result we got, so it has to equal XS of theta. So that's it. Now that might not seem like a lot, but it is. Why is it a lot? Well, because really this tells us everything about how this sort of natural transformation theta underlined is defined. Why? Well, because what do we need to know how a natural transformation is defined? We need to know its components, right? We need to know the nature of the arrow theta underlined subscript V for every object V of our category C. But what is such an arrow? Well, in our case, it's just a function. So in order to know about a function, we just need to know how it works on every input. And what are the inputs for this function? Theta underlined V, theta under arrow V. Well, the inputs for this function are just going to be arrows S from E to V. But we have already that, well, we've sort of proved already that for any V and for any arrow from E to V, any arrow S, we have this formula in red holding. Okay, there's nothing special about the V and the S I decided to pick, so this formula must hold in general. So it basically tells us then everything we need to know about the VEEF component of theta under arrow. It tells us how it works on any possible input, on any possible member of hom E comma V, on any possible arrow S from E to V. It tells us that when we do this function on such an S, we always get X of S of theta. And also this holds for any object V of our category. And so we can use this red formula to understand how theta underlined works, how each of its components works on any possible inputs. So this essentially defines theta underlined. And so that is the nature of this correspondence here. This is how we go from an element theta of X of E to a natural transformation theta underlined from hom E comma blank to X. We just make this choice that we're going to send the identity arrow of E to theta using the ETH component of theta under arrow, and then everything else about theta under arrow gets forced into a particular form by this kind of naturality condition. So that's kind of how we go this way. How do we go the other way? How do we go from a natural transformation, say theta under arrow, back to theta? Well, that's pretty simple. If we have any kind of natural transformation, so let's say we already know what the form of theta under arrow is. Well, then if we just take that natural transformation and take its ETH component and operate it on the identity arrow of E, then we just recover theta, okay? Because, of course, we can always do this. We can always operate the ETH component of our natural transformation on this identity arrow of E, and we'll always get out an element of X of E. And then the fact that that's so means that that's kind of like the signature of that natural transformation, theta underlined. The fact that it has that characteristic means it's forced into a unique form by this previous argument. And so we have this sort of one-to-one correspondence. We can sort of get a natural transformation and grab its signature, or decide on a signature and generate a natural transformation. And so I say that there's this isomorphism here. And, you know, when I'm going from an element theta of X of E to a natural transformation, I write this under arrow. And when I'm going from a natural transformation zeta from hom E comma blank to X, and I want to go the other way, I write zeta dot to denote the kind of corresponding element of X of E. So another way we could say this is that zeta dots is just the ETH component of zeta operating on the identity arrow. So this is really the kind of heart of the Yoneda lemma then, is this kind of correspondence and this idea that we can sort of make this natural transformation theta under arrow by sort of selecting a value theta of X of E. And then we can sort of define all the components of our natural transformation like this. So the VEEF component of theta underlined sends an arrow S from E to V. Well, sends an element. Well, yeah, it sends an arrow S from E to V. So the VEEF component of theta underlined sends an element S of hom E comma V to X of S of theta. Okay. And as I've already said, we can go the other way around as well. Okay. So, all right, that's the sort of heart of the Yoneda lemma. Now, what does this look like in our category of functions then? Well, here's a kind of idea how we can use it. So let's say we have one of these bouquets X, and of course the this object X here, we can think of it as a functor. So we can maybe write it like this: X of E, and then there's a lifted arrow X of S, which sends that to X of V. And we can think of X of E as the set of loops of our bouquet, and X of V is a set of vertices of our bouquet, and X of S is this kind of function which says which vertex a given loop's going to have. So let's say we pick a particular loop of our bouquet, say a loop theta. So in other words, we're saying that we're picking an element theta of X of E, okay? And then we can sort of use this Yoneda lemma idea to find this corresponding sort of natural transformation theta underlined, okay, according to this sort of formula. So basically in this case, what we'd say, well, we want the ETH component of theta underlined to send every element of HOM E comma E, of which there is only the identity arrow of E. So we just wanted to send the identity of arrow of E to X of that element operating on theta. So basically using this kind of idea up here with V is equal to E and S is equal to IDE gives us this formula here. Okay. And then we can simplify this part here because we know that X is a functor. So we know that if we lift an identity arrow under X, then we'll just get the identity arrow. Well, so we know that if we lift the identity arrow of E under X, then we'll just get the identity arrow of X of E, and we're operating that on theta, so that's just going to return theta. So this already tells us that this natural transformation, theta under arrow, is going to send the identity arrow of E, which is the kind of loop in HOM E comma blank, it's going to send that to theta, which makes perfect sense. Okay, if you think about just visually, what would you consider an arrow from HOM E comma blank to X that picks out theta? Well, of course, it's going to send this loop here to theta. And also the rest of the natural transformation is fixed because this holds for any object V and for any arrow S from E to V. So in particular, we can literally think about this case and we get that the V component of theta underlined is going to send this vertex S here to X of S of theta, which is just going to be the vertex of theta here, which again makes sense. So we see that this is all working very well. Now I just want to stress this sort of screen here. This is talking about the specific case of the category of functions, but everything I was just saying about the Yoneda lemma obviously applies when C is any category at all. Well, anyway, let's have a look at another kind of example of this sort of Yoneda isomorphism working, maybe an even simpler one. So now let's suppose that we have a vertex delta of X. Okay, so in other words, let's suppose that delta is an element of X of V. It's a vertex of this object X here in our category of functions. So how would we apply the Yoneda lemma in this case? Well, we'd be looking for a natural transformation delta under arrow, which is like in the Yoneda correspondence with this element delta of X of V. And so the previous kind of thinking tells us that the kind of doing the xth component of delta under arrow on some element f of HOM v comma x is going to give us x of f of delta. So if we just apply this kind of reasoning, we can think, well, we're really just interested in the case where x is equal to v because HOM v comma blank only has something in it when the blank is a v as well. So in other words, we're only really interested in the case where x is equal to v. And in that case, the only element f that we could be working on would be the identity arrow of v. In other words, the only kind of thing in HOM v comma blank is the identity arrow of v in HOM v comma v. And so in this case, this formula, when we use this formula, when x is v and f is the identity arrow of v, it basically just tells us that doing the v component of delta under arrow on idv is going to give us x of idv of delta. Okay, and again, by similar reasoning, this is just the identity arrow, so this just ends up giving us a delta. Okay, which again makes perfect sense. I mean, how are we to think of this vertex delta of this bouquet x as an arrow from this HOM functor, which is just a single vertex? Well, of course, it's just going to be this sort of map here, which points this single vertex into this vertex delta of our bouquet.